Okay, let's do the last couple of problems I haven't had a chance to get to so far. Let's see. So the first one here is we are given this transformation t from the UV plane to the XY plane. It is given by, let's see, so t of UV is given x is equal to u over v plus 1. And y is equal to uv over v plus 1. So the first part here is that we are asked to think about what happens if we set u to be a constant. So that would be a vertical line in the uv plane. U is equal to a constant. What does that get mapped to in the xy plane? Okay, so what we would do here is that we're just going to replace u with constants up here. So x is equal to c, our constant, over v plus 1, and y is equal to cv over v plus 1. We can think of this as some kind of almost parametric equation. X and y are both functions of v. If we replace v with t, it would certainly feel like a parametric function from that part of calculus. We want to eliminate the v. We just want to have x and y, and one in terms of the other. And so here's a little trick that I'm going to do. I'm going to rewrite this y here as y is equal to c times. So what I'm going to do is I'm going to add 1 and subtract 1 here. I'm going to add 1 and subtract 1. So of course that just is, I haven't changed anything. But the advantage here is that I can rewrite this. I can break it up into the difference of two fractions, c times v plus 1 over v plus 1 minus c over v plus 1. Why do I do this? Well, this first term, the v plus 1s cancel, and I just left with c. And the second term, that is exactly that here. And so c over v plus 1 is x. So what do we get here? We see, and this is going to be our final answer for part A, is that the line, the vertical line, u is equal to c in the uv plane gets mapped to the line y is equal to c minus x in the xy plane. Okay, so that is part A. Let's now look at part B. So this is asking us to do the same thing, just with v is equal to c this time. And so we do v is equal to c. Same thing, we're just going to replace, we're going to leave the u alone, replace v with c. So x equal to u over c plus 1. Y is equal to u times c over c plus 1. And here we see, once again, that, so that is x right there. And oops, I circled the wrong thing there. That is going to equal x. So we see that y is equal to c times x. And so this is going to be our answer here for part B. Let me just draw a picture here to illustrate what is going on. So this is going to be in the UV plane. And let me draw axes here in the XY plane. Okay, so what is going on here? For the part A, this was like this vertical line here is u is equal to a constant, and that's going to go to something of the form y is equal to c minus x. That is going to be a line of slope -1 with x and y intercepts at c there. So u is equal to c goes to lines of the form y is equal to c minus x. Meanwhile, so v is equal to c. So that would be this horizontal line here. V is equal to c. It's going to get sent to a line of the form y is equal to c times x. That's supposed to go through the origin. Let me just be a little bit more careful here. Okay. Okay, so that's what is going on here. Okay, so now that was parts A and B. Let's remind ourselves what's going on here. Okay, next up is Jacobian. So for the Jacobian partial xy over partial uv, this is going to equal the determinant of a 2x2 matrix with all of the partial derivatives here. And so it's going to be partial derivatives of x and y with respect to u and v. So we're just going to read off the partial derivatives here. For example, partial x, partial u, we can see it's just going to be 1 over v plus 1. Partial y, partial u is going to be v over v plus 1. And then we'd also have to do derivatives of this x and y respect to v. We'd be using like quotient rule and stuff like that. Let me just go ahead and write down the final answers. It's straightforward enough to calculate a partial derivative. So negative u over, that's a v plus 1 squared, and then positive u over v plus 1 squared. Okay, so when we compute this 2x2 determinant, we get top left times bottom right. So it will be u over, and there will be 3 copies of v plus 1 downstairs. Minus times that minus will give us a plus uv upstairs. And then downstairs will again be 3 copies of v plus 1. We can simplify this because the numerator factors as u times v plus 1 over v plus 1 cubed. And that factor of v plus 1 cancels one of them downstairs. So our Jacobian just ends up as u over v plus 1 squared. Okay, so that was part C here. Okay, let D be the region, the xy plane bounded by those lines right there. X plus y is equal to 3, x plus y is equal to 6, y is x, y is 2x. Okay, so for that part, we're going to go back to this picture right here. That the work from parts A and B is going to be very, very useful here. So 2 of the lines had equation x plus y, x plus y is equal to 6, and x plus y is equal to 3. And those were coming from, as we said, u is equal to 3, and u is equal to 6. Y is equal to c minus x can just rearrange as x plus y is equal to c. The other 2 lines had equation y is equal to x. So like that's y is equal to x. And then the other line has equation y is equal to 2x. So y is equal to x, y is equal to 2x. And those are, again, y is equal to cx corresponds to v is equal to c. So y is equal to x comes from v is equal to 1. And y is equal to 2x comes from v is equal to 2. So what is our integral? Well, so the region of integration, I guess we should say here, is u runs from 3 to 6. This is part D. V runs from 1 to 2. And so now we are ready to tackle, okay, we are integrating over our weird region D. We're making a change of variables. U runs from 3 to 6. V runs from 1 to 2. The integrand was x plus y, but we know that x plus y is equal to u. Don't forget to throw in our factor of the Jacobian, u over v plus 1 squared, dv du. This should be absolute value, but in the region that we're considering, u over v plus 1 squared is always positive. So here's our integral, and my notes tell me I haven't made any mistakes. We get 21 over 2 as a final answer. Relatively straightforward to get there. Okay, so that's one of the two problems I owed you at this